Service endpoints in Azure enable resources within a virtual network to privately connect to supported Azure services, such as storage and SQL databases, over an optimized route. By extending the virtual network identity to these services, endpoints ensure traffic remains within the secure Azure backbone rather than traversing the public internet. They form part of the virtual networking strategy discussed in earlier topics, including subnet configuration and NSGs. While prior settings focused on controlling inbound and outbound flows, service endpoints specifically target connectivity improvements and data isolation for Azure Platform as a Service PaaS offerings, aligning with security and performance best practices. Within the AZ-104 exam, configuring service endpoints is a foundational skill that demonstrates proficiency in Azure networking management. Administrators must understand how endpoints contribute to a secure and seamless hybrid environment, complementing existing resources like route tables, NSGs, and virtual network peering. Having covered core networking concepts in previous modules, the addition of service endpoints reinforces effective routing and fosters better control over data egress. Mastering these configurations ensures administrators can confidently set up secure connections to Azure PaaS services, address compliance requirements, and reduce the chance of external exposure that might arise from default public access methods. Before implementing service endpoints, it is crucial to understand core virtual networking principles covered earlier. Azure VNet architecture divides address spaces into subnets that isolate workload components. Network security groups filter inbound and outbound traffic at different layers. Route tables, whether system-generated or user-defined, dictate message paths between subnets and external networks. Peering establishes connectivity across different VNets by automatically adjusting routing. Each service endpoint leverages these mechanisms, building on the premises of IP address allocation, firewall rules, and controlled exposure. Thus, a solid grasp of these concepts underpins the successful deployment of service endpoints within Azure environments. Service endpoints primarily integrate with Azure services that benefit from direct virtual network access. Common examples include Azure Storage, Azure SQL Database, and Azure Key Vault. The table below outlines several popular PaaS offerings. Service endpoint supported: Azure Storage, yes. Azure SQL, yes. Cosmos DB, yes. Azure Key Vault, yes. When endpoints are enabled, these services accept traffic from subnet-specific private IP addresses, enabling a more restricted access model. This approach complements existing firewall settings, optimizing data exfiltration policies and ensuring your resources communicate across Azure's backbone rather than through public hosts. Service endpoints add system routes within a virtual network, directing traffic to the chosen Azure service through an internal channel. Once activated, requests to the service's public endpoint from selected subnets are effectively recognized as originating within Azure. This mechanism allows your traffic to bypass internet-level exposure and remain in the Azure backbone. The configuration includes specifying which virtual network and subnet can extend its identity to the PaaS service. Most importantly, this integration interacts with the service's firewall or service-level security features, allowing administrators to lock down external access and rely on the filtered internal traffic path. While service endpoints enhance security, they have certain limitations. First, they do not eliminate the possibility of public IP access, though they allow for firewall rules that restrict traffic to endpoint-enabled subnets only. Additionally, they operate at Layer 3, meaning application-level isolation might still require additional controls like NSGs or custom firewall rules. Endpoints are also not supported in every region or for every subscription type, so administrators should verify availability and quotas. Lastly, they differ from private endpoints, which provide fully private IP addresses on resources. Recognizing these constraints ensures appropriate planning and architecture decisions. Using the Azure portal, administrators can navigate to the subnet configuration blade of a virtual network and select the relevant services to enable an endpoint. After choosing a service, Azure updates routing paths automatically. Additional settings can be applied, such as restricting service access to requests coming solely from that subnet. To confirm changes, the portal offers validation checks that display successful endpoint creation. Administrators are advised to verify that firewall settings for the associated Azure service are configured to accept traffic from the newly enabled subnet. This step ensures communication remains confined to authorized private pathways. Service endpoints can also be managed through Azure CLI commands. Below is a simplified example. Bash AZ network VNet subnet update / resource group my resource group / VNet name my VNet / name my subnet / service endpoints Microsoft storage. In this snippet, the service endpoints parameter assigns the endpoint to the specified subnet. Once applied, admins can update Azure Storage Firewall rules by restricting allowed networks to that subnet's virtual network identity. Extending these configurations to other services, like Azure SQL or Cosmos DB, follows a similar pattern by adjusting the endpoint service name and relevant resource properties. PowerShell provides another way to script the creation or modification of service endpoints. For instance, PowerShell set a virtual network subnet config, virtual network $vnet / name my subnet / address prefix 10.1.1.0/24 / service endpoint Microsoft storage. The updated subnet configuration is then passed back to the virtual network object and committed with CITAZ virtual network. Because PowerShell offers parameter-rich cmdlets, administrators can embed endpoint configuration into broader infrastructure automation scripts. By leveraging consistent naming conventions and controlling versioning, administrators can streamline endpoint deployments across multiple environments to maintain alignment with organizational standards and reduce manual configuration errors. Network security groups remain relevant when working with service endpoints. Although endpoints route traffic internally through Azure's backbone, NSGs manage traffic at the subnet or network interface level. Administrators can define rules to allow or deny traffic to specific Azure service tags, such as storage or SQL, to reinforce security boundaries. The synergy between NSGs and service endpoints reduces exposure to only authorized subnets. This layered model ensures that even if an endpoint is misconfigured, a firewall rule can prevent undesired traffic flow. Consequently, administrators retain granular control over inbound and outbound paths, fulfilling robust defense in-depth requirements. Once a service endpoint is enabled, traffic to the associated Azure service is injected into a private route. This means data leaves the subnet, moves through Azure's internal network, and reaches the service while bypassing external networks. By contrast, outbound internet traffic or connections to another region might require alternative routing paths. Thus, administrators should consider how these changes affect logs, monitoring tools, and line of sight into data flow. Any existing route table entries that direct traffic to a virtual appliance or on-premises might not apply to endpoint-bound requests, since they are rerouted directly to the service. When designing architectures with numerous service endpoints, administrators should remain mindful of constraints. Each subnet can support multiple endpoints, but each one places a small overhead on routing tables. Subscription limits might impose restrictions on how many endpoints can be created globally. Additionally, some endpoints might face concurrency or bandwidth limitations imposed by the Azure service itself. While these are rarely encountered in most production workloads, they become relevant for large-scale or high-throughput systems. Proper capacity planning, accompanied by periodic reviews of Azure subscription quotas, helps avoid bottlenecks or unexpected provisioning errors when scaling. Though both virtual network peering and service endpoints handle internal connectivity, they differ in scope. Peering establishes a direct link between two VNets, enabling resources within each to communicate as if they were in the same network. By contrast, service endpoints apply to interactions between a subnet and a particular PaaS service, restricting connectivity to the Azure backbone. Peering is useful for multi-tier applications spanning different VNets, whereas endpoints specialize in private access to public Azure offerings. Understanding the distinctions helps administrators determine which mechanism delivers the best combination of performance, security, and operational simplicity. Azure Private Link and Service Endpoints share a common goal of securing access to Azure services, but they differ in implementation. Service endpoints use a virtual network's existing address space to identify traffic flows, while Private Link assigns a dedicated private IP to the Azure resource itself, effectively placing it inside the VNet. Private Link offers more granular control by allowing traffic from on-premises networks to remain private when connected via ExpressRoute or VPN. Service endpoints remain simpler to configure in standard scenarios. Organizations often weigh the need for fully private resource addresses against endpoint-based approaches that meet basic isolation needs. With service endpoints, administrators can lock down Azure resources to accept traffic solely from selected subnets. This step often involves configuring firewall rules or virtual network filters within the PaaS resource. For instance, an Azure storage account can be set to selected networks mode, adding the authorized subnets. The same principle applies to Azure SQL and Key Vault. This traffic restriction goes beyond default open access, significantly reducing risk by preventing data exposure. Combined with features like managed identity and SSL encryption, endpoints reinforce robust security stances. Administrators strategically layer these controls to safeguard data and application services against unauthorized access. After endpoints are configured, administrators should verify functionality and track performance. Tools such as Network Watcher supply diagnostic capabilities, examining connection routes, and capturing packet-level data. Resource logs within Azure Monitor help document which IP addresses have accessed the PaaS service, confirming that traffic originates from intended subnets. If anomalies arise, analyzing logs for firewall denials or blocked NSG rules can pinpoint misconfigurations. Metrics for latency, throughput, and error rates reveal whether the new routing paths introduce bottlenecks. A vigilant and data-driven approach to monitoring ensures that service endpoints consistently deliver expected performance and reliability. Misconfigured or missing firewall rules typically cause the most frequent endpoint connectivity failures. Administrators sometimes forget to allow trusted Microsoft services, which might be required for certain operations. Another common pitfall is mixing private endpoint features with service endpoints in the same subnet, leading to unexpected routes. Checking effective security rules in NSGs, verifying that the correct service tags are allowed, and confirming registry settings for on-premises scenarios can help isolate problems. Tools like Azure Resource Health and Connection Troubleshoot can identify micro outages or DNS misconfigurations. Short of larger architectural oversights, these checks often resolve connectivity disruptions. When adopting service endpoints, particularly at scale, administrators should align with organizational governance strategies. Role-based access control, RBAC. Policies restrict who can modify endpoints, preventing unauthorized changes. Tagging methods allow classification of service endpoints by environment, department, or compliance requirement. Furthermore, change control procedures ensure that new endpoints pass security reviews prior to deployment. Maintaining a well-organized naming convention for subnets and resource groups helps reduce confusion, especially when multiple endpoints are active. Finally, routine auditing of configuration logs provides evidence for compliance audits, confirming that each endpoint remains in line with defined organizational policies. Many enterprises employ service endpoints to secure sensitive data in Azure SQL databases, restricting access to a series of well-defined subnets. Media companies hosting large video assets in Azure storage can reduce egress costs and minimize exposure by keeping data within Azure. Financial institutions use endpoints, along with NSGs, to protect transaction data flows between application layers. Even smaller organizations leverage endpoints for dev/test environments on a budget, isolating test data while ensuring quick provisioning. These use cases demonstrate how service endpoints provide flexible connectivity options, regardless of scale, industry vertical, or compliance obligations. Service endpoints fit into a bigger networking picture that includes subnets, routing, security tiers, and identity. Previous lessons on route tables and NSGs enhance understanding of endpoint-based traffic flows and security controls. Future modules exploring advanced security, like Azure Firewall or third-party appliances, build on these concepts by extending the perimeter defenses beyond the backbone. Therefore, the knowledge gained from configuring service endpoints seamlessly intersects with broader Azure guidance. From establishing multi-layer protections using Bastion to refining traffic rules in complex architectures. This interconnected approach underscores the cohesive nature of Azure's virtual networking environment in the AZ-104 journey.